Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be going over several examples of Lewis structures. Let's get started. Recall in previous videos, I introduced Lewis structures and how they're the foundation for the overall shape of these molecules that we are going to be determining in future chapters. And so remember, the Lewis theory is involving these valence electrons, and we're predicting what kind of compound it's going to create based on the type of bonding that it would do. It's really useful for us to understand the type of bonding that is possible. And ultimately, we can use this information to predict things like the shape of the molecule and also properties that are affiliated with these molecules. So if you're following along with these videos in sequence, getting a really strong foundation in chapter 9 is essential so that you can learn how to draw these structures. In chapter 10, we're going to learn about the shape of these molecules and compounds that we're dealing with. And then chapter 11, we're going to be looking at what are the properties affiliated with these based on the shapes that are present. So as we get into doing some of the examples, make sure you just keep some of these cautions in the back of your mind. Remember, overall, Lewis theory is predicting that atoms are most stable when they have that 8, those octet around them. However, there are some exceptions that do exist to these rules. Remember, there's a few that can have less than 8, so things like boron or hydrogen or helium. And then there are a number of elements that could actually have more than 8. And so you always want to think when you're developing these Lewis structures, is this potentially an atom that can have more than 8? And if it is, then you can explore different iterations of the structures that you're creating. Remember, you can determine if something is eligible to have more than 8 based on where it's found in the periodic table. If something is found in period 3 or lower, and when I'm saying period, I'm talking about the row 3 or lower, then it could potentially have more than 8 electrons. Now, there are some general rules that you're going to follow and some general kind of schematics that you're going to want to follow. Typically, carbon's going to have 4 bonds around it with 0 lone pairs. Nitrogen will tend to have 3 bonds, 1 lone pair. Oxygen will have 2 bonds, 2 lone pairs. And hydrogen and halogens will typically only have 1 bond. Now, again, remember, with either carbon or oxygen or any of these, none of these are saying that these bonds that exist have to only be single bonds, right? So you may have a combination of single or double or maybe even triple bonds that exist. My recommendation is to always, when you're doing this, you lay out your atoms, assign each one its valence electrons, and make one set of bonds first before you go in and add double bonds or triple bonds. You want to make sure you're not exceeding that octet if not necessary, okay? And so we will learn about these things called formal charges in the future. And those formal charges are really going to help us to figure out which is the most stable structure if we're coming up with multiple iterations. And so you can see some common bonding patterns that are shown for you here. So just keep these in your mind as you are going through some of these examples. So again, some exceptions to be aware of. We know there's that expanded octet. That's for anything in periods 3 or lower. And that is because you have access to those empty d orbitals that we've discussed earlier in previous videos. We also have these things called radicals that could exist. A radical is something that has an unpaired electron in it. You know, normally you see lone pairs around atoms, but if you end up with something that has an unpaired electron like nitrogen monoxide, well, that is something that is capable of creating what's called a free radical, and these are very, very reactive. And there are a few things that have incomplete octets that you'll see occasionally throughout this chapter. And then shown for you here again are just a few more bonding patterns that you may see based on generating some ions and so forth. All right, so let's get into some examples here. And I want you to take a picture of this slide or this part of the video, because we're going to show this in future videos, the formal charge video and the resonance structure video. And we're going to visit this because for some of these, we're going to be able to come up with multiple structures. Okay, and so I'm going to go through those multiple structures in this video, but in future videos, the formal charge and the resonance videos, we'll talk about how we distinguish between them. Okay. So the first question you should always ask yourself when you're doing these Lewis structures is, well, first, am I dealing with an ionic compound or a molecular compound? Am I dealing with ionic bonding or covalent bonding? And so the key that you're going to be looking for is, well, do I have a metal present? If there's no metal present, then you more than likely are going to be doing your covalent bonding, okay? And so if we look at our first example, CO2, no metal present, so we're expecting covalent bonding, all right? Then the follow-up question is, well, which atom goes in the center? How do I know who goes in the center? Well, keep this thing in your mind. The atom with the lowest electronegativity will go in the center. I mean, think about it. You want to put the atom that is more willing to share than the one that's pulling it really tight. Okay. And so who goes in the center is the atom that's furthest away from fluorine on your periodic tables. Okay. Also bear in mind that if you have hydrogen present, hydrogen won't go in the middle because remember, it only has that one connecting point, only one electron to make a pair. So it is always going to be found terminal on the outside of the atoms that you've placed. Okay. So look at CO2. All right, so who would go in the center? Well, we would say carbon. Carbon is the least electronegative between those two. And then for right now, we're just going to be putting our atoms around it symmetrically. We then go about and assign our valence electrons to each atom. So the oxygens will each get 6. And again, notice how I'm putting one of those single electrons towards the center because I ultimately know I need to connect to that carbon. So it doesn't make sense for me not to put anything towards the center. For my carbon, I'm going to give it its 4. And at this point, this is where we can now go in and make our set of single bonds. So we do one set of single bonds between each of these different atoms, and we step back and count. Around the carbon right now, we see a total of 6. And around each oxygen, we have 7. And so by doing that quick count, remember, we're counting not only what's on them, but what they're sharing. That lets me know, well, hey, I haven't met my octet. So what could I do to satisfy it? Now, it's at this point where you explore options such as creating additional bonds or potentially even transferring, moving an electron from within one atom to another within this overall compound. And you'll see that will become an option for some of these. All right. So in this case, I wouldn't want to transfer anybody. I wouldn't want to take from the carbon and give to oxygen or take from oxygen and give to carbon because still not everybody would be satisfied. And so what I can do though is move these electrons to create an additional connecting point, an additional bond. Again, we do one at a time. And when we do that, we see that we now have 8 on this oxygen here. We have 7 on the carbon. And so our oxygen on the outside is still not satisfied, nor is our center carbon. So we can bring those additional electrons toward the center. And now we create another connecting point or another bond. When we step back and count at this point, everybody now has 8 valence electrons surrounding it, whether it be through sharing those bonding pairs or the lone pairs that are there. Okay. All right. For the next one, SeOF2, who would go in the center? So you should say Se should go in the center. It's the furthest from fluorine, followed by oxygen and fluorine on the outsides, symmetrically for right now. We give each atom its electrons. So fluorine would get 7. Again, notice I'm putting that single electron towards the center. Selenium will get 6. So I put at least some going towards the atoms I got to connect with. And oxygen also will get 6. Okay. And we make a set of single bonds. Like so. And step back and count. Around the oxygen on top, we have 7. Around each fluorine, we have 8, so they're satisfied. Halogens are always the easiest to fulfill. And then around selenium, we end up with, well, it had 6 of its own. I'm sharing 3 more. We now have 9. Now, we should always check real quick. Is selenium somebody that can have more than 8 around it? And indeed, when we look on our periodic table, again, we're looking for period 3 or lower. We see selenium is in period 4. And so what that tells me is that there is a possibility that this atom could have more than 8 electrons around it. However, it doesn't mean it has to. Okay, so just keep that in mind. Well, now we look at where we're at, and we see that our oxygen does not have enough. The selenium has more than enough, right? And so we can think about what are some options here. Well, one option somebody might say is that, well, could we just give the electron from selenium to oxygen to make it 8? And yeah, that is a potential, right? But does anybody see something else? Some of you guys may say, well, what about making a bond, right? Rather than giving it to oxygen, since I know selenium can have more than 8, what about we make a double bond between them? So I'm going to redraw this just so we can explore both of those options. Okay, so I'm going to try to draw it similar to how it's already drawn out for us so we can compare. And then we have here. All right, so we're here, right? Draw this a little bit better. Okay, so one option some of you guys may say is, okay, well, let's give an electron. Let's take an electron from selenium and give it to oxygen, okay? And so if we do that, and of course, we'd want to move these two to make a pair on the bottom. So if we do that, well, that now gives our selenium a total of 8, and our oxygen also has 8. And so that seems to be a good solution. We have our octet being met. But you could also, because selenium is one that can have more than 8, rather than give it to oxygen, I can move that electron towards the center and make a double bond instead. And again, we're just going to pair those up because electrons like to be in pairs. And now if we do our count, well, we see around the oxygen up top, we have 8, so the octet is being met. And selenium now has a total of 10, and our fluorines each have 7. So which one is correct? All right. So come back for the video about formal charges and resonance structures, and you'll be able to find the answer to that, okay? So I'm just going to leave that here, but ponder that. Which one do you think is correct? And why? Why would you think it's correct? Okay, make your guess now, and then again, check your answer when you get to the resonance and the formal charge video, okay? All right, let's try NO2 minus. So for NO2 minus, who would go in the center? That would be our nitrogen, furthest from the oxygen, from the fluorine, excuse me. And then we're going to put our oxygen symmetrically around it. Now, we haven't dealt with this a charged species before in this material. However, we treat it just like we've seen it before. That charge is simply going to mean that we have an additional electron if it's negative, or we're taking away an electron if it's positive. And so in this case, because it's a negative, that means somewhere in this, we have to show that we have an additional electron. So we start again by giving each element its atom, or each electrons. Okay, so each one gets 6. Then for the nitrogen, we have 5. And then we have this extra electron. And you can throw that extra electron wherever. I may, gather and say, okay, I'm going to throw it on the oxygen. Okay. And then we start and make our first set of bonds. So set of single bonds. And we count on the bottom, or on this oxygen to the left, we currently have 7. On the oxygen to the right, we currently have 8. So that's good. And then the nitrogen in the center, we have 1, 2, 3, 4, 5, 6, 7. Okay. And so what options can we explore for how to get this to 8, that octet? And we also double check, we see nitrogen is not one that can have more than 10. And so that's going to help to kind of drive what we're going to do. And so the option here is to actually go ahead and move that electron that appears to be by itself towards the center to create another bond. In doing so, we end up with 8 over here and 8 over here. And overall, we would enclose this entire thing in brackets with a negative charge, okay? Now, I want you to think about this. This structure could have been drawn another way, okay? So think about, how would you draw this another way to still satisfy all, to have 8? How would you draw this another way, okay? That structure that you're going to come up with is what's known as a resonance structure. So again, we'll touch on that in future videos, so make sure you guys come back. But just think about, how else might you draw this? And then once you come up with that other way, which one would be more stable? Are they equally stable? Again, that answer is going to be answered in future videos. All right. So let's move on to the next one, H3PO4. So for this one, who goes in the center? Well, it would be our phosphorus. And then we're going to put our oxygens around it symmetrically. And then now we add the hydrogens. Again, symmetrically. They're terminal. They go on the outside. Same pattern applies. I give each one its valence electrons. So hydrogen would get 1. Oxygen would get 6. Again, I'm using X's and O's just to help you all see the difference in the electrons. You all are welcome to do dots, hearts, whatever you so desire, as long as you can count them, or whatever your teacher says. All right, and then phosphorus is going to get 5, okay? So then we go through and we make a set of single bonds. And so again, connect between each atom, make at least one connecting point using 2 bonds, and we step back and count. Around each of the hydrogens, we now have 2. Around each, at least these bottom 3 oxygens, we have 8, so they're happy. Again, I'm counting the lone pairs and the bonding pairs. Around the phosphorus at this point, I have a total of 9, and I check. I do see that phosphorus is in group 3, or excuse me, period 3, so it means it could potentially have more than 8. And then my oxygen right now only has 7. So how do we go about making sure that we can get both of these to a stable position? Well, similar to what we did in the SeOF2, you could transfer 1 to the oxygen as an option, which would then take our phosphorus to only having 8, and our oxygen would now have 8. Or you could also, and I'm just going to draw this in the corner, we could have instead created a double bond between, I'm running out of space there, let's try that again. Okay, so we could have also created a double bond between the oxygen and that phosphorus there, which would then give us a total of 10 around the phosphorus rather than 8. But we know that is possible because of the fact that phosphorus is found in period 3 or lower. So again, which one is more stable? The double bond or the single bond? Again, check back on that resonance and formal charge video to learn the answer to that, okay? Now, SO3 2-, there's a lot of different ways you could come up with this. I'm only going to show one in the interest of saving space. All right. But again, come up with as many options you can. In the next video, you'll be able to check to see which one's the best. So again, we check to see who goes in the center, would be my sulfur. And I'm going to put my oxygens around here, 3 of them. I'm going to give each atom its electrons. So each oxygen gets 6. And the sulfur also will get 6 to start. And I'll put at least 3 towards the oxygen. Okay, put at least 3 towards the oxygen. And we do 1 set of bonds. So connect and connect and connect. Okay, we'll step back and count. Around each oxygen, we now have 7. And around sulfur, we see that we have 6 of its own sharing 3 more, so that would be a total of 9. We do see again, sulfur is one that could have more than 8 around it, so just keep that in mind. All right, and think about, well, what could we do? How could we make this stable? Well, one thing you may think is, well, let's just go ahead and make a double bond somewhere. Let's bring one of these oxygen in and make a double bond. Now, you guys should be screaming at me and saying, wait a minute, we forgot something, right? What we realized we forgot are these 2 extra electrons. So make sure that you tack those on somewhere. I'm going to throw them on my oxygens here, just so we can take count of them. But you guys make sure you put those on before you start doing all your bonding, okay? And so in fact, around our other oxygens that have those extras, we have 8 and 8 that are present. Okay, draw that a little better for you guys. Okay, and so what that now gives us is a total of 8 around this oxygen and 10 around the sulfur, which we know is possible. Now for this one, you could have come up with a number of different options. So come up with as many as you can. And again, future videos, check that resonance or formal charge video to see which one is the most stable. Okay. And then last but not least, we have P2H4. Again, those hydrogens are going to be terminal. They're on the outside. And so I'm going to start by putting my phosphoruses by one another, and then put the hydrogens surrounding it. And for right now, I'm just going to put them here and here. All right. And we're going to give each one its valence electrons. So each hydrogen gets 1. Each phosphorus gets 5. And again, putting those single points towards where they're going to make connections. And we make a set of single bonds. And we see that everybody is now satisfied. Each of those hydrogens have 2, and then the phosphorus has 8 around it. I hope this video helped you guys understand the basics of doing Lewis structures for these covalent bonding molecules. Make sure you guys like, comment, and subscribe, and be sure to come back to those resonance and formal charge videos to learn how to distinguish between these possible structures that you're coming up with, okay? Have a great day, and I'll see you guys in future videos.